I talked about gross domestic product and its problems, and I'm now going to talk about alternatives to the gross domestic product as indicators of economic activity and economic welfare. I'm going to start with the theory of the environmental product. And the question is, how do we bring the natural environment into our indicators? The definition of the gross domestic product is that it's consumption plus investment. And the main problem with this definition is that it includes additions to the physical capital stock, but it does not include subtractions from the physical capital stock. And therefore, people have introduced the net domestic product, which is consumption plus investment minus depreciation. The intuitive definition of the environmental domestic product is analogous to this. We have consumption plus investment in the physical capital stock minus depreciation of the physical capital stock, and then we add investment in the natural capital stock, and we add subtractions from depreciation, from degradation of the natural capital stock. So this is the amount of nature environment that we lose in a particular year, and this is how much nature or environment we gain in that particular year. This is pretty intuitive, but it actually goes back deeper, and there's a better justification than just, oh, it looks the same. And that goes back to the work of a young Marty Weizmann, who you see displayed here, looking smug. What we want to do is we want to maximize net present utility. So we take the stream of consumption from now until infinity, we take the utility of that consumption, and then we discount it back to today, and then of course we want to integrate over the whole thing from now until infinity. So that is what we want to maximize, net present welfare. But of course this is not an unconstrained optimization. What we have is that the change in the capital stock, K dot, equals the depreciation plus the investment. And then there is another constraint, namely that total output follows from the production function, but I substitute it into this constraint and say that investment equals total output Y minus our consumption C. And I assume that output Y only depends on one factor of production, namely capital. That's a simplifying assumption just to keep the notation simple and the derivations palatable. So this is what we want to do. Now, this is a maximization problem in continuous time. And the reason for that is that solving a problem like this in continuous time is actually easier than solving it in discrete time. I know full well that you're more used to looking at optimization problems that are discrete, but believe me when I say that continuous time actually has its working in continuous time actually has its merits. So how do you solve an optimization problem like this? Well, you start by forming the Hamiltonian, and this is the current value Hamiltonian. And the Hamiltonian is defined as H, and H equals the objective function, or rather just the current bit of the objective function, so just UC. You do away with all the fancy stuff, you do away with the discount factor, you do away with the dt and the integral, and you just keep your current objective, U of C. And then you add to that the shadow price, but this is optimization in continuous time, so we don't call it a Lagrange multiplier, but we call it a co-state variable. It's just the same thing, it's a shadow price. And we multiply that with not the right hand side minus the left hand side of the constraint, but just the right hand side of the constraint. So we just have K dot here. So compared to the Lagrangian, this Hamiltonian actually is a lot simpler. We just take parts of the objective function and we just take the, I said right hand side, but I meant the left hand side of the So that is what you need to do first, and then we have two first order conditions. They are displayed here. The first order condition is that the first partial derivative of the Hamiltonian to the thing that we decide on, and that is how much we consume, so dHdc must equal 0. dHdc is actually pretty simple. This is just the first partial derivative of utility to consumption, so this is marginal utility, U sub C. K dot, the lambda times K dot, if you derive that to the C, that is pretty simple too. K dot does not directly, does not immediately depend on C, but if we substitute this thing here in here, K drops out, Q of K drops out, so we just have the minus C, so we have a minus 1, so this plus lambda K dot becomes a minus lambda, and that should equal 0. So essentially this equation says that the marginal utility of consumption should equal the co-state variable, should equal the shadow price of capital. And that makes intuitive sense because capital is if you invest, you essentially increase future consumption, so that the shadow price of capital, the marginal value of capital, should be equal to the marginal utility of consumption. Makes intuitive sense. So that is this expression here. That's the first order condition, the static first order condition. The dynamic first order condition of a current value Hamiltonian problem is that the change in the co-state variable minus the discount rate times the co-state variable equals the first partial derivative of the Hamiltonian to the state variable. Now this is perhaps a tricky expression, but we actually don't need this in this particular analysis. We're just going to focus on the static condition of optimality. What do we have here? We have that the Hamiltonian, and this is just the definition, right? The Hamiltonian is U of C times plus lambda times K dot. We now have an expression for lambda, namely that is marginal utility. So the Hamiltonian equals our current utility plus the marginal utility times the change in capital, right? Because we know the lambda, and that becomes U sub C. This thing here is approximately equal to the marginal utility times consumption. This is just the first order approximation of our utility. And so this expression here is an approximation of our Hamiltonian. Now we bring UC to the other side of the equation, and what we have is that the Hamiltonian normalized with UC, U sub C, with marginal utility. So this is, Hamiltonian is really utility. This is measured in utility, right? This is measured in utils, and the shadow price of capital is also measured in utils, right? Or rather, it's util per dollar. So this expression here is in utility. This expression here is now in dollar terms, or in pound terms, or in euro terms. And this thing here just is equal to consumption plus the change in the physical capital stock. So this the monetized and the linearized Hamiltonian is the net domestic product. It's C plus I minus D. So that is the justification for using the net domestic product, or the net domestic product is where the emphasis should be. It is just the monetized version of the Hamiltonian of our welfare problem. Now, there's a pretty powerful insight by a young Weizmann. An older Weizmann added nature and conservation into the equation. So now we assume that our utility function doesn't just depend on our consumption, but also depends on the natural environment N. We still have our equation of motion for capital, that is, the change in the capital stock is how much we depreciate plus how much we invest. But now we don't just consume, but we also invest money into nature conservation. B, of course, that money disappears. That cannot be used for other purposes. So that is our first constraint. We have a second constraint, namely that the change in the natural environment depends on the natural processes that are there. It may be that the environment is bouncing back, it may be that it's shrinking, depending on the size of your theta, or the size of your theta. But we can make nature better by investing P. So the theta is just what is going on in nature, has nothing to do with us, but the P is what we do, and the P can of course be positive as well as negative, right? It can also be extracting things from nature, as if you're mining for coal or whatever, right? We solve this by forming the Hamiltonian. The Hamiltonian is the same as it was, except that the utility function now also depends on n. Look, we're still just using the current value. We still have co-state variable times the change in capital. Now we have another equation of motion. So we have another co-state variable, mu times, and this should be an n dot here. Right? That's our Hamiltonian. So we take the first partial derivative to consumption and set that equal to 0, and nothing has changed here, right? This is just the same expression as we had, and the first order condition for dynamic optimality is also still the same, but we're going to ignore that one again. But we have another set of first order conditions. We need to, because we're also deciding on our P, we're deciding on how much we are investing in nature conservation. So the HDP should also be equal 0. The HDP is N depends on P, right? So we have the U, the N, that's U sub N. And then, of course, we need the chain rule times the N dP. So that is one thing that we need. But then we also have this thing here. What we need for this is also mu times the N dP, right? So we have this particular expression here that should equal 0. And then we have the dynamic condition as well that we're not going to use. We're going to apply the same trick as we just did. We're going to take the Hamiltonian. Just going to play that back again. This condition here implies that lambda equals uc. So that is this thing here. This lambda becomes a u sub c, and the mu, in order for this condition to hold, we have that mu must equal u sub n. So we can also get rid of the mu and replace it by the marginal utility of environmental quality, or the size of the environment, or whatever you want to call it. So we have this expression here. This thing here we can still linearly approximate with marginal utility times consumption, so nothing has changed there. This thing is as it was here, and what we do here is that we pre-multiply it by u sub c over u sub c. So we pre-multiply it with 1. So nothing has changed here either. Then we bring uc to the other side of the equation, and we have again gone from a Hamiltonian in utils to a Hamiltonian in dollars or in pounds or in euros, and that equals consumption plus the change in the capital stock, so investment minus depreciation, plus the change in the natural environment times the marginal utility of nature over the marginal utility of consumption. So this is essentially translates your natural environment into monetary terms. That is what this does. So along the optimal path, the monetized linearized Hamiltonian equals the net domestic product plus the monetized increase in nature, or if need be, the monetized decrease in nature. And this is the environmental product. We monetize our changes in the environment, we add those things where we improve the environment, and we subtract those things where the environment got worse. So that is the justification for the environmental domestic product. So this is theory. Nordhaus and Tobin in 1972 proposed in a much more ad hoc way something very similar. They called it a measure of economic welfare. And they stressed that it's a measure of consumption rather than production. And they said that the measure of economic welfare is the gross national, the net domestic product, bad mistake here, minus all the economic bads, like things that you're just fixing things or you're controlling pollution and really has no other reason than to prevent harm, minus the regrettable necessities. They said, well, police and defense and all those things is all well and good, but really we would like to live in a world without police, or rather we would like to live in a world where the police is not necessary because everybody is well behaved and sticks to the law. Those things do not really contribute to economic welfare. And then they added household production, subsistence agriculture and illegal production, and they also added measures of leisure. And of course, this is a form of household production. You're sitting in front of the telly enjoying yourself. That is a form of that is producing welfare, but not necessarily one that is captured in an economic transaction. If you sort of have a contract that allows you to watch as much telly as you want, but you're not paying by the minute, and very few people do. They emphasize that this measure is primitive and experimental. As I said, it is entirely ad hoc, but it is very influential. Nowadays, nobody uses the measure of economic welfare anymore, as proposed by these two gentlemen, but people use very similar indicators called the Index of Sustainable Welfare, or the Genuine Progress Indicator, or the Sustainable Net Benefit Index, or the Measure of Domestic Progress. And there's all sorts of things that people, all sorts of different names for essentially the same thing. An important thing to keep in mind here is that there's durables as well. It's not just that our economic well-being depends on consumables. And for durables and for capital goods, including human capital goods, including natural capital goods, they argued that you should be using the annuity of the services delivered by these durables and capital goods. And here we see a somewhat older study that uses essentially this particular index renamed as the Genuine Progress Indicator. That's the GPI that you see here. And what you see is that it matters. This is for the United States from 1950 to 2004, and whereas GDP per capita keeps increasing. These gentlemen argue that if you look at, if you correct particularly for environmental issues, then actually the economy has not grown, but it has stabilized since around 1974. There's all sorts of issues with this measure. An important one is the valuation, because an important part of this whole accounting is that you're depleting the non-renewables. You're depleting oil and coal and gas and all sorts of metals and what have you, and that somehow needs to be valued, and that what needs to be included is the true value and the true scarcity value, not just what you get on the market. Also, if you're destroying nature, that should be included. If species go extinct, if forests get cut down, that needs to be included. And previously we talked about the issues with monetary valuation of these things, that they are plentiful and it's hard to get these numbers right. And there's also issues with the cumulative nature of a lot of environmental damage. Some environmental contaminants linger in the air or in the water for a very long time, and sometimes these things accumulate, and sometimes there are current problems that manifest themselves at the moment depend not just on what we're doing it now, but depends on all the things that we have done in the past. And a little bit of lead in the environment isn't bad, but if there's already a lot of lead in the environment, then adding lead is actually pretty bad, and not nearly or much worse than just adding that little bit of lead would do to a pristine environment. But the problems that manifest themselves are therefore the result of the accumulation of past emissions. Now, that is true for today, but it's also true for the future, which then in turn mean that the net present value of future problems, and as I said, we want to include an annuity of durables, and if stocks of environmental contamination accumulate in the environment, then that essentially becomes a capital good, or capital bad is perhaps a better word. But then the value of that annuity then depends on future actions, because how bad future lead problems will be depends on future emissions of lead, and that makes the whole thing very contingent on future actions, and you have no idea whatsoever what future people are going to do, and that makes it just very difficult to put a solid number on that. There's also all sorts of arbitrary distinctions in here. What expenditure is exactly defensive? You can look at, you can take a cycling helmet and say, well, that is a defensive measure, doesn't bring me any utility whatsoever. That is a purely defensive expenditure to prevent harm to my head should I fall off my bike or be driven off my bike. But you can also see a bike helmet as a fashion statement, and there's definitely people who do that, and then it becomes a consumptive expenditure. So these distinctions are arbitrary. You need to make assumptions about, if you're including measures of inequality, how bad do you think inequality really is? And because of this arbitrariness, you can massage these numbers up or down. Very important to emphasize that these indicators, genuine progress indicator, the measure of economic welfare and all its variants, are essentially measures of weak sustainability, because essentially what you do is you're adding up and subtracting capitals as if they are addable and subtractable. You assume that you can substitute the deterioration in the natural environment with an accumulation of man-made or human-made capital. And that is an important thing to realize, that that is what this is. And that immediately implies that if you're really interested in strong sustainability and you're interested in the state of the environment per se, not as what it delivers to humans, then you actually cannot use these particular measures, because they simply do not measure what you think should be measured.